Okay, the next module is concerned with writing applications in C++ for finance. And we've got a number of sections which deal from beginning with a high level to the level of actually writing code for finite difference methods and Monte Carlo. And the first section is called Applications for Computational Finance number 1. So it's an overview of all the attention areas you have to get involved in general, and in the next coming years, or for the course as well, when you develop C++ code for applications and computational finance in particular. So let's have a look at the goals of the section here. We want to apply C++. So you've learned C++ up until now, starting from C, object-oriented C++, advanced object-oriented, generic programming. You've done STL library, a little bit of Boost library as well. So we want to put all our knowledge together to actually write some applications, small applications, because it's a student course in that sense, to get you prepared for university degrees and so on. So it's useful to know. But basically, we want to learn a bit of design, so write decent software. Hacking has its place, but if it becomes a habit, you'll get messy code. So we want to implement the code for which is accurate, so you want to get good results, and efficient as well. Okay, and a little bit of design and analysis, as I've said, although it's not the main concern because it's not part of the course. But I would like to say something about it, because when later on you go into industry or banking, you will be designing software which has to be industrial strength. So you have to do a bit of design, quite a lot of design and coding. And one of the objectives is to become a good programmer. So if you're writing code which crashes all the time and so on, it's not going to be very good. Now, some tips for students and for anybody, I suppose. People tend to be perfectionists. Before they've finished one problem completely, they're on to the next problem. It's like a bit of a research project. So this is not in that sense, a university brainstorming academic conversation. We've got certain objectives. We want to solve the problem. So we get the problem solved. You may not be able to do it in one go. You never can, actually. You never get it right first time. So you have to be aware of this fact, in my opinion, and do it in a series of increments. So get something working, whatever that's supposed to mean. Maybe get an example of get it working would be that you get the good results. But maybe the software is not so pretty as you'd like it to be. Later on you get it right, so you design it to make it more flexible, and afterwards you get it optimized so it really runs fast and it's brilliant, and it's dare I say it, you've documented it a bit. Okay, so before we start on developing applications, let's just look back on C++ and the knowledge you need, the skills you need before commencing. So it's just a checklist. So we check what knowledge we need, and so you need to have some the 80-20% rule. So 20% of your knowledge, roughly speaking, will produce 80% of the efficiency and effectiveness of your application. Of course, the Visual Basic, Visual Studio C++ environment, you have to be able to resolve compiler errors as quickly as possible, and so on, linker errors. So you need a little bit of mathematical background, numerical background, algorithmic background, and quantitative finance before commencing on the course. So how would you actually get some knowledge? By studying a bit, looking at the actual papers on pricing options, Google, and so on and so forth, Wikipedia. So this is not a PDE course or a Monte Carlo course or a finite difference course. It's just too big. There would be no time. Of course, you're always welcome to contact me if you're interested in finite differences and so on. But basically we will be applying C++ to such problems. So there's a little bit of forward reference in the sense that I'm assuming you know a little bit about the underlying maths. So it's 20-80% rule as always, nearly always. Okay, what are the top skills you need to have, in my opinion? First of all, well, it's fairly simple. Everything is data and functions. So you've got to know how data is created in memory, stacked memory, heap memory, how it's allocated, how it's used, accessed, modified, and so on, and destroyed. Now, in particular, the STL containers are going to be very useful, and the corresponding algorithms. You can make your own data types, but you've got to be you've got to feel fairly good with the actual manipulation of data. We got different kinds of functions, global functions, member functions, function pointers, of course, and function objects. These are absolutely vital in applications because you model all your algorithms using functions. And of course the third step is how data and functions combine. So you've got data and functions, and different ways of doing data and functions. You've got classes, of course, you've got structs, you've got namespaces. You also need to know about pointers, not necessarily down to the level of pointers to pointers and all of the low-level C stuff. As I've said, it's not necessary, I would say, for you just at the moment, and maybe it's not necessary as either for many applications. You've got to know about const input arguments, const return types, const member functions, and so on, and how they all relate to each other. The next set of skills is you've got to be able to create robust classes. So in other words, what we talked about in the course, and also to be able to discover and define classes, because most of the applications here will correspond to classes which work with each other to solve a certain problem. STL you need to know a bit about. It's called the STL vectors, iterators, of course. Some of the algorithms I've talked about. A bit of boost is useful as well, because as I've said, for example, we won't be creating our own random number generators. We'll be using the generators from boost. Design. You've got to know what inheritance is and be able to apply it, and to know when not to use inheritance, because inheritance can be bad. And we've got composition. It's aggregation. So you build up objects from smaller objects. A very important principle is the following. It's called the SRP. It's the single responsibility principle. If you develop a class, the class should do one thing pretty well. So you've got classes which have a number of responsibilities. It becomes unmaintainable, because when you change one responsibility for whatever reason, all the other code will need to be changed. So you'll get a kind of entropy or fallout in your code. And it makes it less reusable. So this is a very important feature, and I would adhere to it if at all possible. So, and later on we'll have a class called option, European option class, which just contains the data corresponding to options and the corresponding functions, like the price of the option, deltas, and so on. This is a very general remark here, which is maybe not applicable to you guys at the moment, but when you develop applications, or any application in fact, we try to break the application up into subsystems. Just let me draw a little diagram. We're not going to be doing it in the course because it's a C++ programming course, but let's say you want to solve a problem. Decomposition has been known for the last 50 years. So you might have a problem. I've got input, some input, and I've got some output. So it could be a huge function. Probably at the moment many of you are using MATLAB, for example, and you just create one big monolithic application. Whereas with system decomposition, I break my system up into subsystems. So the information flow is coming in here, of course. it's going to the next level. It's being transformed, and eventually your output is the same here, you see. So we've broken my system up into subsystems, and we analyze and design and implement each subsystem independently of the others. Of course, they'll have interfaces, inter-subsystem interfaces, so it makes life easier. So you can develop each subsystem independently, rather than rather than solving one big monolithic system in one go. Again, it's another facet of the SRP, single responsibility principle. This guy here is too big, so we break it up into the input scanner, let's say, the part of the system which processes the input. Here's the part which does the actual processing, and here's the output. This was a very well-known paradigm when I was very young in the last century. Input, processing, output. It's a good paradigm to use. Okay, what are the problems when you start developing applications? And it's just an overview, so I'm not saying you're going to need all of these techniques, and you're going to apply all the techniques in your course here. What I am saying is that they are important, and you'll see bits and pieces of them when you start developing software. You have to pay attention to certain areas. So this is like in learning a new skill. And software design and implementation is a new skill. It's not something just because you know mathematics or physics or whatever that C++ is easy and programming is easy. On the contrary, software development is much more difficult than mathematics, in my opinion. Maths is relatively easy, kind of, if you know it, but software development is so difficult to get it right. Okay, so the problem dimensions. What are the let's say attention areas we need to look at? What kinds of applications are you going to be working on in computational finance in general, but also in the course? In our particular case here, we'll be concentrating on equity options. It's a good way to start. Possibly a little bit of interest rate modeling and so on. One-factor models. So you've got one underlying stock price. We will do two-factor models like basket options a little bit, exact formula. We also need numeric algorithms, because most problems don't have an exact solution. You have to employ some numerical algorithms, and the numerical algorithms we'll be talking about are finite difference method, Monte Carlo and lattice methods, like the binomial method, trinomial method. And we have software design and implementation. So being a good software designer, that's something which takes to be a good software designer maybe 50 years, 40 years maybe. Well, let's say 20 years. You get better as you go along. The next step is using C++ libraries. We're not going to reinvent the wheel, certainly not in this course. So you'll be using libraries from STL and Boost to make you more productive. And we have to use C++ with the applications. At some stage, you're debugging and testing, so you're actually you write your code, you don't get the right answers. Something's wrong. It may not compile, it may not link. That's your first problem. So you have to get a running program, after which it might crash or it might run, but the answers are wrong. So you've done something wrong. So you have to debug it and test it and so on. Just look at the code and see that you've done the right algorithm. So so it's like a hierarchy of classes and functionality. Let me go back to my. So we start with basic C++ knowledge, which I've talked about. At a higher level, you got the STL. Then we had the Boost libraries. We build blocks, for example, which use Boost libraries, and eventually we'll have the application. This is a general way of designing software. It's maybe not so interesting or relevant at the moment for you, but at least you've seen it once. So we'll discuss each of the topics in more detail now, starting with the range of applications. So the main interest is in one-factor methods, as I've said, option pricing, equity, fixed income. So if you can program a one-factor Black-Scholes using exact solution, finite difference Monte Carlo, lattice method, you're doing okay, in my opinion. Other applications are interpolation, numerical algorithms, and so every model you'll be applying has its own advantages and disadvantages, like efficiency. Finite difference method is very fast. Monte Carlo is a bit slow, but it always works, for example. So we talk about numerical algorithms. We need building blocks for your application infrastructure. So I don't want you to write your own cumulative normal distribution function or whatever, your own matrix or your own vector classes. Just use them from the course. These could be in Boost, STL, or somewhere else. When we actually do software design, this is a big topic. All I can do is just do one slide, but you take it in phases, and these could be iterative and incremental. Don't adopt the how should I say, without making you annoyed, don't try and optimize it immediately and get the most beautiful and most generic result possible in the beginning. It never works that way. Always get something running. So if you're solving a problem, don't worry about the nice input-output GUIs and maybe nice object-oriented inheritance, but just make sure in particular that your algorithm is correct, and you can always make the algorithm more flexible and so on. So the whole point about it is, for example, if you're doing an option pricer in finite difference, that the results are correct, and later on you can make it more flexible. And getting it right means building in more functionality, so the different kinds of solvers, different kinds of options, and so on. And get it optimized, you make it beautiful with frameworks and design patterns. And this takes a lot of, this is a full-time job basically, but ask anybody who's been working as a quant for a number of years will tell you. So it's a 10-year plan, and you should ask yourself, you're doing something, where do you want to be in 5 years? Okay, we'll be using C++ libraries. Ideally, you have to make a distinction between what you know, what you want to know, what you're good at, and what you don't want to do or know. So in other words, it's called outsourcing. So the STL vector class, for example, you don't want to write your own vector class. You just want to outsource. So you concentrate on your core business, whatever it might be. In my particular case, I would be concentrating on one particular aspect that's called solving finite difference methods or PDEs using finite difference methods. So that's what my background is. I did my research in industry, numerical methods with the finite difference method, finite elements. So the other stuff like data structures, which I've made myself, but I prefer to use STL and Boost now. There aren't, relatively speaking, there aren't very many C++ libraries around compared to Fortran, for example, or maybe R or some other language, or Gauss or something. But so you either have to make them yourself or use them. Another option is to wrap Fortran code in C libraries, C wrappers, and call the C wrappers from C++. Some companies do take this approach, but for you as a student it may not be relevant at this moment in time. It's if you can wrap Fortran code in C and C++ and call the libraries, I think you'll get a job. Okay, so C++ and its use in applications. Just a general remark, means C++ is an all-round language, systems language. So it's good for everything or it's good for nothing. It just depends how you look at it. Compared to, let's say, Fortran. Fortran was specifically made for algorithms. It's called formula translation. COBOL is another language. It's called common business language or something. Business-oriented language. So you can use for application development. It's not the most ideal language, in my opinion, for certain areas, but it's probably the best all-round language at the moment. There are other languages like Java and C#. They have their own advantages. So, but in general, use the most appropriate tool for the job at hand, which is what you're doing. So when you're working, you've got to be careful about what are you making? Are you making a painting, or are you making a frame? Some people make the painting and the frame in one go. It doesn't work. So you make the painting. This is really your core business, and the frame will come later. Debugging and testing, that's a big topic. You can use the code review. Just print out your code and have a look at the code to see that you've done it properly. You've got to be able to solve compiler and linker errors, of course, and Visual Studio has a debugger as well. You can trace variables, start a debugger in the Visual Studio environment. I think it's you make debug points, breakpoints in your code. You can actually debug it. You have to create your project in debug mode as well, because it stores debug information. The debugger is kind of outside the scope of the course. So here, to summarize my different layers and what I'm talking about, we talk about the quantitative finance applications. Then you go to going around. Well, it's not sequential. Finite difference methods. These are solutions. We go to design of the problem. We need data structures as well. We need libraries. We need algorithms. The algorithms are part of your core business. And we implement it in C++ and we do testing. So this is a very general structure. And this is something that it'll take you, will occupy your waking hours in the next X number of years. If you decide to continue writing applications for quantitative finance applications or any applications. At the moment, let me just give my own personal view of the status of what everything is. Most people do Monte Carlo. It's fairly easy. Very few people are doing finite difference methods. PDE, relatively few. The design is most people don't design really as such. Or they've got no tools to communicate about design. Algorithms are fairly well established, of course. You see all the articles, and C++ as well. So for you guys on the course, the focus is on C++, but in the future you can carry on programming, sometimes called hacking under certain circumstances, but it's important to pay attention to the bigger picture, and this is kind of the bigger picture. The resources, books, Claylaw and Strickland is an old book from 1998, but it's very good because it contains pseudocode which you can map to C++. So that's very useful. It contains the actual code, pseudocode plus the algorithms plus examples. So you can write the same examples in C++ and compare with Claylaw and Strickland. In fact, this would be a very good idea. The book by Glasserman and Monte Carlo, Hull, of course. The books by Paul Wilmot, if you're more interested in the PDE approach. I've got a number of books on the C++, including a beginner's book, advanced book, Monte Carlo, and a book on finite difference methods. And the web articles, of course, Wikipedia, on different kinds of prices. So you have to do a bit of research when you're working on this part of the course. So there's less, how would I say, hand-holding, but more look around for the formulas. So you can build your application based on published articles. So it's probably what people do in MATLAB anyway, so maybe I'm telling you something you already know. Okay, we're finished with the introduction part. We've discussed a bit of everything. What can you expect? Let me put it that way. Maybe you won't be confronted by everything I've talked about in the course. You probably won't, but you will later on. And whether you do it or not, that's another question. But these are the attention areas. So I just thought I would give an overview before we start going into real pricing stuff. So we give an overview of what's to come when you start programming C++ applications. It's a multi-dimensional, multi-layer problem because you get all sorts of attention areas. So it's a global preparation, so get prepared for the rest of your career. So we'll take a break now, and we'll go to the next section in a moment. So see you later.